We are welcome to our eighth session on embodied carbon today, August 9th. Before we get started, I thought today was also a day that the IPCC put out their report on climate change and the physical science related to climate change. And so I thought it was important to kind of highlight this, that, even if we started sharply cutting emissions today, total global warming is likely to rise around 1.5 degrees Celsius within the next 2 decades, a hotter future that is now essentially locked in. So we're at a point where we really need to start emphasizing carbon and energy and all the other climate change factors in our designs. And so that brings us to the reason we're here. We're here because we want to encourage companies, individual firms to sign up for the 2030 commitment. There are a lot of myths that it takes too much time, or it might require too many resources, or if you have poor performing projects, you shouldn't sign up. But in reality, it doesn't take that much time to gather the data if you do it as you go. The program is free. All the data is anonymous. So even if you have poor performing projects, it's helping establish a benchmark or a baseline to work from, so you can continue to improve. And it really is something that you do as the project progresses. The project doesn't have to be finished, and you don't have to achieve the target reductions. You just have to start documenting where you are, because you can't manage what you do not measure. And so it's really important that you become a 2030 signatory firm. So it's really a 5-step process, technically 3, because all you're doing is signing the commitment letter, creating a sustainability action plan, and reporting the projects in the DDX. And then, the next year you're endeavoring to meet the targets. And 3 years out from the day you sign, you're reviewing and updating that sustainability action plan. So that's really all that's required. We do have a bunch of resources available. All of the videos that we do as part of the 2030 commitment or the working group are up on a YouTube page now, where it's organized in playlists. So it's much easier to navigate than the Vimeo platform was. We have all of our 2020 sessions that were digital on Zoom uploaded there. And then we also have all of the sessions from 2021 there, along with other monthly meetings of the COPE committee. There's also a guideline for how to create a sustainability action plan that's available online. And we're going to start offering office hours on a first come, first served basis. So Monday, August 23rd, Bunny, who's on the line today, will be on Zoom from 5 to 6. If you have questions, you can just log in and ask any questions. If you need help with the DDX or signing up, that's what this time is going to be most useful for. We're also going to hang around after the session today if anyone has any questions. Okay. Oh, meant to delete that. So let's get started with embodied carbon, tools for tracking. So the learning objectives today are to define what is embodied carbon and put it in context of the other metrics that are related to carbon and its role in decarbonizing the building industry, and finding design strategies or important contributors to reducing embodied carbon. And we're going to also dive into tools around using tracking embodied carbon. And hopefully all of this will help you understand where you can start intervening on your projects to track embodied carbon and produce better buildings. So we have 3 speakers today. We're gonna kind of give 20 minutes for the embodied carbon 101 section, tools for tracking, and then we have a project example or a series of project examples that helps illustrate how to get started with embodied carbon. And then we're going to leave the last 15 minutes for questions and answers. So please, if you have any questions, you can put them in the chat box at any time during the session. And we will do them at the end. So our speakers today are Stephanie Carlisle. She's from this senior researcher at the Carbon Leadership Forum. And we also have Kayleigh Houde, who's an associate and computational community leader at Buro Happold. And she's going to be presenting the BOM tool, which is spelled BHOM. And lastly, we have Devki Desai, who is actually a structural engineer at HOK. And with that, I'm gonna stop sharing.
Oops. One reminder to folks while you switch screens, if folks can sign in, I just posted a Google form to receive AIA credit. Just sign in using the form and we'll submit that so you get your CEUs. Thanks.
All right, Steph.
All right, how does that look? Can you guys see my slides okay?
Looks great.
Yeah, it looks all right. Okay, great. All right. Thanks, everyone. It's really nice to be able to come talk to this Philly AIA group. I'm really excited to introduce, I think what I'm mainly going to do is do a little level setting first. So I'm going to introduce the topic of embodied carbon and then also do a super brief introduction to life cycle assessment. I'm going to try to not get too in the weeds on LCA, but I think it's really important for folks to understand what this analysis process actually is, where the data comes from, what it's tied to, and at least kind of give everyone an equal footing in this topic area. So first, I'll start off by just talking a little bit about embodied carbon. What is it and why does it matter? Okay, so what is embodied carbon? Embodied carbon refers to greenhouse gas emissions arising from manufacturing, installation, maintenance, disposal of construction materials. So these are all of the different emissions associated with making, using, and disposing of building materials across the whole life of your building. So embodied carbon is tracked across that full life using a term called global warming potential. So this is one thing to get out of the way first. I'm going to use the word carbon and carbon emissions throughout this whole talk. I think some of the other speakers probably will as well. But when we're talking about embodied carbon, we really use that as shorthand for all of the different emissions that lead to global warming and climate change. So that would include methane, that includes NOx, that includes lots of other gases that we track, but we don't want to track all of those different individual chemicals, or we don't want to keep track of them individually. So often we're going to compress this down to global warming potential, or GWP, which is often expressed as CO2e, and that little e just means CO2 equivalents. So for the whole rest of the talk, I'm just going to call that embodied carbon or carbon emissions. So in order to truly decarbonize buildings and the built environment, we really need to talk about both operational and embodied carbon. So we call this generally taking a total carbon perspective on our projects. And that really means looking across this full project life. So I'll kind of walk through all of these different steps of carbon emissions. But effectively, the cradle to gate embodied carbon in the beginning of the life of making the actual building materials and putting them together. The operational carbon, which is, I think, what you have largely been talking about in this group in terms of operational carbon, but also energy efficiency, et cetera, fuel uses, as well as end of life embodied carbon. So all of those are part of this total carbon picture. And I think what's really important is just to be grounded in, as Devki, I'm really glad you started the presentation today, just reminding us that what we are really talking about is a desperate and urgent climate change situation, right? So it is just, wow, this weather is really intense today. So I think that it's important to remember that embodied carbon is significant, it is urgent, and it is really important that we start addressing it on every single one of our projects. So often the number that gets tossed around is that the buildings tend to account for about 40% of energy-related carbon emissions. That is true and really important and significant. But also what this slide does is really zooms out a bit further and just calls attention to how much the building sector and industrial sector are completely intertwined. So even when we think about emissions outside of just energy-related emissions, there's really no way for us to decarbonize the global economy or decarbonize the planet without really taking the embodied carbon of buildings really seriously. So you might think that you have, architecture is sort of a limited and small industry, that we don't have a lot of power. But I would argue that the decisions that you make on every single project, every single day, extend into building operations, into industrial emissions, into transportation, into agriculture, into all of these different sectors. So we really have a lot of power to make a difference. Reducing embodied carbon is also urgent, and we really don't have any more time to be taking these emissions for granted. So while architects have long focused on reducing operational energy of their projects, and hopefully now are paying much more closer attention to operational carbon and fuel choices more broadly, embodied carbon has really been pretty overlooked by most practices. And I think for a lot of designers, this is a fairly new topic. But it's simply the case that in order to meet or even come close to any global targets of holding off 1.5 degrees of warming, or even 2, 3, 4 degrees of warming, we must reduce those embodied carbon emissions immediately. So not in 2050, not at the end of our building lives, not after years and years and years of energy reductions, but immediately. So it puts extra pressure on this question that often is talked about as the timescale of carbon. The concept being that emissions we put into the atmosphere right now matter a lot, and arguably matter much, much more than emissions 10 years, 20 years, 30 years out. So I don't mean to say that operational carbon is not important. It is, and it is essential that we get the energy consumption and the resource use of our buildings down. But if we're ignoring these huge pulses of carbon that happen before our buildings are even occupied, that's this big yellow bar all the way on the left, all of that upfront carbon, then really we're not going to make any dent in carbon emissions in the future. So when you think about kind of a standard performance building, if we think about the emissions that'll happen before 2030, a really critical time for us to be targeting and thinking about our total impacts, probably about 70% of the carbon emissions of your project is completely connected to embodied carbon. Right? And if you're just kind of reducing your operational carbon by 5%, 10%, 20%, you're really just tinkering around the edges. And by the time you get to a really high performance building, let alone net zero or passive house, of course, all of the emissions are wrapped up in embodied carbon. Right? So this is really a topic we need to be thinking about on all of our projects. Third, I just really want to underscore that embodied carbon is also a really, really important climate justice issue. Embodied carbon disproportionately impacts frontline communities, poor communities, communities of color. When we work to reduce embodied carbon, we're also working to eliminate the environmental and public health burden placed on frontline communities that suffer most, both from the global impacts related to climate change and the local impacts related to fossil fuel use in transportation and manufacturing across the construction supply chains, like smog and diesel emissions. So whether American communities or global communities in American supply chains suffer, we're accountable for those negative and sometimes deadly health climate impacts as well. Luckily, there are a lot of strategies at our disposals and a lot of things that you can do on every single project that you work on to address embodied carbon in your work. On any given architectural project, you have the ability to make use of and explore all of these strategies that I think we're going to touch on today in the different project examples you're going to see. Kind of break them down here into 3 main buckets. These are, they're a little squishy. You could break this down a number of ways, but you can think about first ways that you might optimize for carbon on the whole project. So these are questions and thinking you're going to do generally pretty early in a design project, and that's making use of strategies like really just using fewer materials. So building a material reuse, reduce floor area, design for disassembly, thinking about what the flows in and out of the project are. And we could put that under that category of building and material reuse or right sizing. Second, we have a whole bucket of categories around optimizing the systems and construction typologies. That's where we're exploring alternative materials, so low carbon materials like bio-based products and assemblies, as well as, again, thinking about the material efficiency of what we are actually building with. And generally, we're going to be making use of whole building life cycle assessment during that phase and to explore those types of strategies. And then finally, optimizing procurement. So this tends to be about strategies that emphasize clean manufacturing. So efficiency, fuel switching, what we would call low carbon products, et cetera, and sustainable sourcing. And to really evaluate those claims and strategies, you're going to be making use of environmental product declarations, or which are really, I'll explain those a little more in a second, are specific life cycle assessments of products and materials. I don't have time to, and I hope that in another session, we can really talk about policy and embody how this is spreading across the whole industry and the whole country. But I just really wanted to touch on the fact that in North America, there is a growing body of embodied carbon policies that are requiring reductions in embodied carbon on projects. So we really hope and encourage that architects and engineers and consultants can really take leadership on this topic. But it's important to know that if we don't, we will largely be regulated into this. So there's a lot of different approaches that are being pushed and a huge amount of momentum that's growing in terms of figuring out how to really compel design teams to address this area, because the voluntary pathway hasn't really been working. So to be frank, but it's really exciting to see a whole series of federal buy clean laws, state procurement bills, as well as lots of local legislation that is spreading across North America. Many of these different policies focus on clean procurement and material selection, or product selection, I mean. But we're also starting to see a growing momentum to address embodied carbon in building code using whole building LCA, as well as, hopefully we can talk about in the Q&A, some of the push for voluntary reporting and disclosure, like including embodied carbon in the AIA DDX, as well as the ILO-5 system and other national databases. But in general, we could break down these different strategies. And I think what we're going to talk about, I think we're going to cover both of these with all of the speakers today. I generally think of as a building approach, which uses whole building LCA tools or early design estimators, and a material approach. So if we really, really want to simplify it, and it's really not an either or. I would encourage project teams to start thinking about which one they can make use of, which tools can support these workflows, but also how to make use of both, right? And which strategies are really going to empower you to make a difference on your actual project. Whether that is embracing low carbon concrete specifications and writing those into your design documentation, or doing early phase analysis and comparative analysis and really making perhaps even more significant embodied carbon reductions on your project. But I think both are really valid, and both are things that we're going to address on this call today. Okay, so that is a very fast overview of what embodied carbon is, how we talk about it, how we report it, and getting some of the terms out of the way. So I now want to spend just about 5 or 10 minutes talking about life cycle assessment. So how do we actually measure embodied carbon? And what is actually happening in these software tools? Where does the data come from? So the ways that we talk about and evaluate embodied carbon on design projects, as well as across lots of other industries, is a practice called life cycle assessment. Life cycle assessment is an analysis practice. It's been around for about 40 years, so it's not new, but it's quite new to our industry and the design community. So LCA is really an evaluation of all what's happening within these models, is an evaluation of all the inputs, outputs, and then the potential environmental impacts of a product system across its whole life cycle. So like I said before, that's going to start all the way at material extraction, look at manufacturing, look at construction, use, replacement, et cetera, and then also allow users to think about end of life, design for disassembly, material recovery, et cetera. So another way to look at that, to think about that whole process, is what we call life cycle stages. This also is a really good vocabulary to start getting comfortable with, because it's how we report carbon across a building project. So we tend to break up these models, and all of the tools that you might use will do this a little bit differently, but we'll use these standardized life cycle stages, which are set by the ISO standards. So, and you'll start seeing these terms when you're looking up embodied carbon data. So material manufacturing, that sometimes people use the shorthand of A1 through 3. That's generally what is covered by a lot of environmental product declarations. And we would tend to refer to those as cradle to gate assessments. So that's just going to look at how is this material made and what were all the impacts associated with it up until it leaves essentially the point of sale. So this is not including the full life cycle of the product. When we move into a cradle to grave assessment, we're really looking at all the materials, energy, water, all of those impacts associated with this full life cycle. So that would include construction, it would include use, end of life, and then this lovely category called Module D, which allows us to think outside of our individual projects. And you take all of those inputs and outputs in the model and then think about and allocate the different impacts in terms of their emissions to soil, to air, to water. So this is going to let us think about the effects on global warming potential and climate change, but it's also going to give you a lot of feedback on other environmental impacts. So impacts to such as eutrophication, which is pollution in our water systems, acidification, air pollution, other types of toxicity. So I think sometimes we lose track a little bit of the other environmental impacts that go into life cycle assessment. And in general, underlying these different processes is some pretty simple accounting, right? But the devil's in the details. So what you're really doing is gathering an inventory of all the materials in this whole building or a product or assembly, multiplying it by the impacts and getting a total of environmental impacts. So sounds simple, but when we think about the complexity of how buildings come together, this form of accounting is obviously much more complicated. So just to walk you super quickly through what's happening in the background of a lot of these data and tools that the other presenters are going to talk about is really this process of inventory and impacts assessments. So the first step is kind of moving from chemicals to materials. The diagram on the screen is giving an example of how we track in the background data all of those different processes that go into making what look like pretty simple products. So this is a comparison of some of the system processes behind an XPS rigid panel versus a soy polyurethane spray foam, for example. So it's a good example because it's one where the elements that are huge contributors to climate change or global warming potential can happen at different points, right? We want to make sure that we're thinking about those really, really carbon intensive blowing agents like R134 that are happening with the XPS manufacturing in the factory. But we also want to think about the blowing agents that are happening on site with spray foams, for example. So LCA tools are going to help bring all of that information together. The next step often is that we don't just pick materials or individual chemicals, but we're also thinking in terms of assemblies. So LCA databases and tools are going to help bring all of those different materials together. So this is a diagram of an LCA model built up of a SIP wall, pretty simple multi-material assembly. And similar to the way we can think of other types of performance, we're also going to start thinking about that in terms of the flows and all the environmental impacts associated with how all these individual materials come together. And finally, when we're thinking about whole building LCA, what you're ultimately getting to by using design integrated tools really is getting accurate, quantified material estimates or a bill of material of all of the different materials coming together in your project, right? So fundamentally, what most LCA tools are doing is actually helping designers make that translation, right? Between the way we draw assemblies, the way we specify or think about assemblies, and all of the different actual quantities of materials behind them so that we can do robust analysis. That's really the fundamental work of tools like Tally, of OneClick, or Athena that are going to help architects make those translations so that you can get environmental impact data right in your design tools and not have to be doing all of the background modeling or doing all of that quantification by yourself. So I think we'll show a couple different examples of what that looks like, but there is a really diverse range of tools that are starting to aim to meet every design delivery pathway and design process that designers are doing, whether you're in an integrated Revit integrated workflow, a Rhino integrated workflow, or working out of spreadsheets, hopefully there's a tool that you can start looking at embodied carbon in your projects. And finally, I just want to mention, maybe this will come up in the examples or in the Q&A, one huge topic that folks are really grappling with when they're new to LCA is, what do I measure, right? A huge differentiation between different tools that are available also has to do with scope and the scope of assessment or the system boundary of some of these models. So some tools are really just looking at structure. Many folks who are doing whole building LCA are extending that out to look at structure, at enclosure, at interiors, and other kind of elements that are starting to join the fray, like looking at building systems and MEP, site work, landscape, et cetera. So I think there's a way in which the practice of LCA needs to become more accessible through tools that are easier to use, but also tools that cover a much broader system boundary, because we really can't know which elements of our projects have the most impact or where we have the best opportunities if we're simply not measuring or modeling those building systems. So a huge example that I think maybe Kayleigh might end up talking about next will be MEP systems, which have long been excluded from scope, but are really, really, really important. So running out of time here, but I just want to throw this slide up mostly for folks' reference. As I mentioned, there are tons of LCA tools. There are many more being developed as we speak. The ones on the left are really more professional LCA tools. Most designers don't necessarily make use of these tools. That's the kind of modeling I was showing examples of, where you're going all the way back to material engineering or chemistry. The two columns on the right, both the design integrated whole building LCA software is like Tally or BOM or Athena or OneClick. Those are ones that are aimed to work mostly with assemblies themselves and building materials. So they're doing a lot of that translation that's really going to help you integrate embodied carbon calculations into a design workflow. But I also just want to call out that there's a ton of free carbon calculators. I think all the ones on this list are free, and many more that are in development right now that are looking to ask really specific questions. So whether it's letting you do takeoffs for specific concrete mixes, like ZGF's excellent free concrete mix tool, or looking at early phase LCA, like EPIC or BEAM, which is specific for residential, EPIC, which takes a total carbon perspective, or to build or not to build, which is starting to look at renovation, restoration, and this really tricky and interesting question of whether you should do energy efficient retrofits on existing buildings or build new net zero buildings. So lots of cool tools to look out for and to try out on your projects. And finally, I just want to end with kind of this little breakdown of just talking for a second about how really what we need to get to is one in a workflow in which embodied carbon questions are not asked at the end of the project, but similar to the way I think you're building a conversation in this group about energy modeling and other forms of analysis, that is something that tracks through the entirety of the project. That early on, you want to be using tools that are allowing you to set benchmarks, to ask questions really early in the design phase, to think about where you're going to have the most impact on your project, to do hotspot analysis. During design development and construction documentation, you're getting much, much more detailed and thinking about optimization and really tracking all of those different trade-offs between embodied carbon and operational carbon, and then really hoping to get more and more practices to that space where they're really taking those design models and analysis and putting it into the documentation for their project, making sure that if you have great ideas and concepts about embodied carbon reductions, that they actually get built, right? So that's really getting into that world of specifications, tracking, reporting, and disclosure. So I will leave it at that and pass over to Kayleigh for the next presentation.
Thanks, Steph.
Thank you so much, Steph. That was amazing and a great segue to Kayleigh's presentation. She's going to do a deeper dive into the tools.
All right. So Steph, great intro. And I think you actually listed more tools than I even have on the slides here, but there are more coming out every day. So as you saw on Steph's slide, there are so many different tools that we could, potentially look to start doing LCA studies, but you might say, okay, so where am I supposed to start? What's the right tool for me? Hopefully we give a little bit of detail about each of these tools. So some questions you might have is, what's the cost associated with the tool? Where does the underlying data come from? That's a really important question in this space. When in my project should I be using different LCA tools? Like Steph mentioned, it's better to do it at the beginning of your project when you can have the most impact versus, your past CDs and you're just wrapping up analysis at that point. So better to kind of do it earlier on. Some tools are better for that than others. Which life cycle stages am I interested in studying? So like Steph mentioned, A1 to A3, that's usually what EPDs cover, but it's an important question to take into account. And which environmental impact categories am I interested in studying? Am I just interested in global warming potential or embodied carbon, or am I interested in all of them? So those are some of the questions that you may start off with. The way that we've looked at this at Buro Happold, since we are a global firm, we use lots of different tools. So each of those tools listed across the top are tools that we have looked into or utilized on projects. This is our internal matrix that we go through in terms of which tool should we be using for which job. So here we see that Tally is listed, as well as Athena, OneClick, EC3, BOM. And we tend to look at different decisions here in terms of where the data came from. Is it specific to the US or the UK, since those are our two main offices? Is the data updated regularly? Which life cycle stages does it cover? So this is just a bit of kind of looking into how we choose to do LCA studies and looking at all the different tools. But if we start to look at kind of like the macro level, one tool that's very close to home for Philadelphia, obviously, is Tally, originally created by Kieran Timberlake, which is local to most of you, which is a great tool because it's integrated with Revit, which makes sense for so many of our workflows. It allows you average values with some customizability, informing those big picture designs on your project. So earlier and earlier, we're starting off with Revit model, so it makes sense to have a tool that's kind of sitting there for you to help you make design decisions, and it's very much a plug and play type of system there. So Tally is a great one to start off with. Also, if you're interested in looking at a more micro object by object types of decisions, EC3 is a great one, recently integrated into BIM 360 through Autodesk. So this allows you to look at individual products. So it's very specific, and it allows you higher resolution of those individual case by case, let's say one concrete versus another one manufacturer versus another, but allowing you to see those kind of industry average values as well as where the individual products fall, which is very useful. Also, OneClick LCA, we actually see a lot of our UK folks use this tool in our sustainability and physics group. This allows you very specific data sets, allows a wide range of data sets, lots of different regional. I know there are a lot of French EPDs in there, but this one again is very much plug and play, very specific to the products that you're specifying, and it actually does include scopes like MEP, which is valuable. But again, each of these tools takes a slightly different methodology on what Steph showed is a fairly simple calculation. It's just more a matter of what are you trying to study? What's the data that you're trying to look at? And then BOM, which is the Buildings and Habitats Object Model, is an open source tool that was created by Buro Happold, open sourced a few years ago. This is a fully customizable tool that's able to be used whether you're modeling in Rhino, modeling in Revit, or even you just have an Excel spreadsheet of your different quantities. It's capable of accessing a variety of different open source data sets. So EC3, Oakpadot, which is a German data set full of information, Quartz, which was a project by Google Flux a number of years ago. Lots of different types of data sets being integrated there, but it allows you very much object by object, you're seeing what you're attaching as EPDs. The use of this tool in particular comes at the increased cost of computational competency requirements. So if you love Grasshopper, or you love Dynamo, or you're really interested in assessing an early stage Rhino model, this is the right tool, but I would say that it is more complex in some ways and easier in others. So I'm going to go a little bit deeper into how the methods are set up here, just so you can see kind of the underlying logic, which would be the case for any of these tools. But since this one is closest to home for me. So what is BOM? It's an open source, so free means of accessing collective industry expertise through computational methods. You'll see them as nodes in Grasshopper, Dynamo, or Excel. We have 30 software adapters that allow interoperability. So if you're trying to go from Revit to IS to do an energy model, there are interoperability forms of doing that. Adapters are what we call them. So that's part of what BOM does. We also have individual toolkits like the LCA toolkit that allow us to solve wicked problems like climate change. So starting to look at what this might look like, please don't be scared if you hate Grasshopper or hate looking at nodes. But something like this is how we look at the whole project lifecycle assessment. So a lot of the times we were looking at these kind of benchmarking studies and saying, you know, what level of LOD was that project that that benchmark was based on? And there wasn't enough data to give us that information, or where was the project located? What was the type of project? Those are usually included. But things like, you know, which primary structural material did you have? A lot of those important questions, we tried to get those down into our LCA scope here so that when we were comparing projects later on, we would know they were apples to apples and you weren't comparing the wrong things. We also were very specific about the way that we were quantifying each of those different scopes of work. So if you do an LCA study by the book, structures, foundations, and enclosures are kind of the top 3 bits, since they tend to cover, I think, the majority of the embodied carbon of the building. They're, you know, the highest mass of the building. So those tended to be focused on, and MEP and tenant improvements kind of forgotten about, but we have included them in our methods just because it makes sense to have everything there. If you have it, you may as well study it. So for structures, slabs, core walls, beams, columns, easy. Structures, you know, such an easy scope to be able to cover. You have so little to cover there, and it's so high in volume that it tends to be the highest embodied carbon. But then if you start to look at all of the different pieces here between structures, foundations, enclosures, MEP, and TI, you're seeing the rest of the building kind of come to fruition, and you can start to focus on other bits like ceiling tiles or finishes, and MEP looking at refrigerants and ductwork and piping. So being able to look at the holistic picture here. Again, we wanted to be very specific about what was included in these studies. And this is just showing you how you would actually start to have your objects, so something like a bar or a beam, and you're actually attaching the data, the EPDs, to the individual object. So this bar would be plugged in as an object here, and then the fragment that's attached to it, that is the actual EPD. So this is EC3 concrete, 0 to 2500 PSI in strength. So actually taking those objects in your model, so floor, column, a wall, a beam, a duct, and attaching the EPDs to them so that you can work with them through the rest of the LCA study. Each of those EPDs is then broken down into a common language. So these are all the properties that an EPD usually contains. So each of those has a quantity type associated with it. Am I measured by volume, meters cubed? Am I measured by mass and just kilograms? Everything is in metric, which is nice for us all to speak one language except for Americans. So a little bit of a learning curve, but that's kind of across all EPDs as a whole. Also just looking at which life cycle assessment phases are covered, generally A1 to A3, because that's all the manufacturer can control. We also have things like descriptions, the amount of global warming potential, the amount of eutrophication potential, anything that was contained in the particular database. And then you kind of want to look at the level of granularity that you have on your project. So if you're really early stages, projects in the US, you have a Rhino model where you have kind of mass-based geometry, applying something like quartz data set, which is really kind of rough, regional, industry values rather than being a very specific manufacturer's product, it makes more sense to apply that type of data set at early stages when you're comparing massing versus massing, or you don't want to get to the specifics of a particular type of concrete necessarily. You're kind of saying concrete or steel, those kind of larger picture decisions. So quartz is great for that. And then once you start to kind of move further along into DAD and CD, when you have a more fleshed out project, using EC3 or Okpadot, something like that makes a little bit more sense. So in terms of how you would actually assess the life cycle assessment, you can do that by individual object. So column versus column, you know, one is bigger than the other, so it'd have more embodied carbon, or scope. So structure scope versus structure scope, or structures versus foundations versus enclosure. Where should you be focusing your energy and your decision making? And then finally, evaluating the entire LCA once you have all of those scopes pinned together. So that's what these look like in the individual little nodes there. We also have lots of error handling here. So saying, hey, I didn't actually find any foundation scope piles in here. I didn't actually find XYZ, whatever you didn't include. So making sure that we're very aware of what we didn't have as a part of the project is really important. Again, when you're looking at benchmarks, it's important to know, hey, they didn't actually include, you know, their slabs for structures. I don't want to compare myself to that particular number. I think we get so hung up on numbers sometimes as an industry and saying, well, what am I comparing this to? Well, you want to make sure you're comparing it to a similar size project, similar scope being studied. So if you did include MEP, you don't want to be penalized for that. So when you're comparing to another project, maybe don't include your MEP scope, something like that. But just making sure that we're aware of what can be included. And then also looking at our results here. So just plugging in the entire LCA and studying something just like global warming potential. I just want to look at the embodied carbon of the overall project and being able to look at that and actually push those out to something like a server like Mongo or SQL or wherever you're storing data, so that we can start to do these really interesting studies of one project versus another and kind of starting to make better decisions. And just a little bit of an example of what this might look like. This is some rhino geometry being studied over here and being able to give you kind of a red, yellow, green we've done in some cases to say you really should focus on the, I don't know, the slabs, or you should really focus on the foundation walls because they're very, you know, intense in terms of embodied carbon. And then also looking at a little bit of dashboarding to see, again, scope by scope, where you should be focusing, which EPDs you're using, so that we're able to look at these on a kind of micro level as well. That's all I had.
Thank you so much, Kayleigh. That was amazing. So on deck now is Devki, who is going to do a deeper dive in to structures and different ways that they've intervened on structures projects across a couple of different examples at HOK. So I'm going to be sharing the slides. And all right, can everyone see my screen?
No, not yet.
Oh. No? How about now?
Yes.
All right, thank you.
Thanks so much, Devki, and thank you to Josh as well for inviting me. Can everyone hear me all right? Yes? Okay, great. Okay, I apologize in advance for some background noise if there is any. I'm in a cafe right now. Actually, Devki, I was wondering if I could request control, and maybe that'll save you from having to flip through my slides.
Yeah, go ahead.
All right, let's see, how do I do that?
So it'd be at the top. or like wherever you're.
Click view options if you have that. Request remote control on the flyout.
Thank you so much. Hi, Brian.
All right, you're good to go.
Devki.
Thank you so much. So let's see if this works. If my, I'm not sure that's working.
It might lag with the internet connection, but there you go.
Oh, there we go. I'm wondering if there's a way I can go backwards to the intro. Oh, there we
Okay.
go. Thank you so much. Hi, I'm Devki from HOK in New York City. It's a real treat to be invited to an AIA Philly meeting, so thanks for looping me in. I learned a lot from the 2 previous presentations, so that was amazing. Thank you so much. So we can skip this slide because this was covered in detail. I'm going to see if I can click through. This was also covered in detail. I'm going to talk about life cycle analysis. So skipping right forward to this, this is how we think about life cycle analysis helping us through our structural projects. We are an AE firm, so we work really closely with architecture and MEP and the sustainability team. And so this is an example of how we together try to reduce the embodied carbon from a baseline. This is a sample, this is a graphic that I had put together for one of the clients to just explain why we were doing life cycle analysis on their project. I'm sure many of you have kind of mulled over what you want to use as your baseline building for various projects. It's a tricky decision to make, but I can touch on it really quickly here. So you see this reduction from a baseline, and the question is, well, what is the baseline? It is defined by LEED to be a building of similar size, orientation, function, operating energy performance, but also similar typology. So what is the business as usual building for that's comparable to what you're designing? Sometimes, especially at firms that many of us work at, the project is so incredibly specific, it can be hard to nail down what exactly the baseline building is. For example, for LaGuardia Airport, or for a very specific university hospital with really stringent vibration criteria and a lot of other specific needs that we're designing to. So sometimes for projects, we choose the project itself as we have designed it at concept as the baseline from which we want to improve. So let's see if I can click through. Just clicked, there might be a little bit of a lag. There we go. So this is something I'm going to glaze over as well because Steph and Kayleigh went into much greater detail than I'm going to go into. But there are lots of LCA, oops, I clicked too many times. There are lots of, thanks Janki. There are lots of LCA tools available to you. Some are great for concept, some are geared towards CA. We tend to use one-click LCA most of the time. And then also just to put a little bit of more empowerment into your hands, you can do a life cycle analysis by hand in a spreadsheet if you so choose. So it's not something you have to rely on a black box to do for you, but we like to use these programs because it facilitates managing a large amount of data. So we can go to the next slide. Okay, there we go. So this is just a look into one-click LCA, which is the tool we use most often. If anybody is curious and just getting started on doing life cycle analysis, we typically start with Revit if we have a Revit model. If it's too early in the design process, we'll use our material quantities spreadsheet that we've likely put together for cost estimating purposes or for the client anyways. Typically you'll do this in SD. So you can start with Revit or you can start with a spreadsheet. Either way, you just format it for whichever tool you're using, you upload it, and there are various data sets you can draw from if you don't have suppliers selected yet, which early in the process, typically you don't. So there are lots of national databases with regional specific and national specific data. So here's a quick look into where does all this data come from. Some of the data that you're using, and when I refer to data, I'm going to refer back to Steph's presentation where she discussed EPDs and the impacts, which is what you multiply by your quantities to get your total environmental impacts. So those emissions factors, which might be CO2 equivalents per meters cubed of concrete, or it might be SO2 equivalents per meters cubed of rigid insulation. Whatever those values are, those emissions factors come from, they can come from national databases like NSF, ASTM, NREL, or they can come from suppliers who have uploaded their EPDs. They've provided their environmental product declarations to the software developer. And then of course, when you get your EPD from your supplier, you can use that as well or upload it to the program that you're using. So concept phase. So how do we do life cycle analysis in concept phase to inform our design? Let's up to the next slide. There we go. So this is an example of a concept phase LCA that we did in our San Francisco office for a typical office building. This helped us get a sense early on how far we, whether we're within striking distance of our carbon reduction goals. We're trying to get to, I think, 65% reduction in embodied carbon by 2030 and 100% by 2040. I think those are the updated goals. It used to be 50% by 2030, 100% by 2050. But I think those have since been updated because we didn't meet, I think as a global society, we didn't meet our targets. And of course, there are many warming feedback loops that we're now seeing. So we're on a much more aggressive timeline than we even initially thought. So are we within striking distance of those? This really helps us narrow down which materials we want to use for a given project. As you can see, mass timber was ahead of the pack for this building, but it really depends on what your loads are. This is an example of an embodied carbon reduction on an existing building. We're really trying to encourage clients to renovate existing buildings instead of starting from scratch. That's a really great way to reduce the carbon intensity of a building per unit area. So this quick study that we did for a university in New York, their campus, was that they would save 5.5 million kg CO2e just by renovating their building instead of starting from scratch. Maybe that's not what they wanted to hear. Maybe they couldn't wait to see the brutalist concrete building gone. But what we were able to calculate for them is it would be much better towards their own university carbon reduction goals to embrace the brutalism and renovate the building. So this was discussed by Kayleigh in great detail, what they do at Buro Happold. We also do parametric LCA calculations in-house at HOK. This isn't something that we have made available to the public, but this is a little glimpse into how we do the parametric calculations during concept. You have your drop-down menus of different regions and different types of concrete, for example, and your environmental impacts out. This is another glimpse into our concept phase. Our concept phase carbon reduction procedure. So sometimes we want to look at multiple objectives at the same time. So with a couple coworkers, I developed a multi-objective optimization tool. There are many different ways to do this. There are many different academic and professional groups who have gone down this path. And the nice thing is it provides you with a family of solutions for to meet both your embodied and your operational goals. So we can keep going. And we have kind of baked in some in-house steel, concrete, and mass timber databases for this multi-objective parametric tool to draw from. So that was concept. Moving into design development and construction documents, this is an example of the carbon reduction process for a large university hospital project. This is a carbon tracker that I put together for the clients so they could see in almost real time what the implications of their design decisions were. So we're putting the power back in the client's hands to decide how they can reduce their own embodied carbon. And oftentimes when we're working with university clients, they have really aggressive carbon reduction goals of their own that they're trying to meet. So I think this was really fruitful for them to be part of the process. What we did on this particular project is our first big carbon reduction design strategy was we collaborated with the geotechnical engineer to move from a temporary earth retention system to a permanent earth retention system for a project of this size. That was fairly doable because the earth retention system required for construction was already quite significant. So it wasn't that much of a jump in terms of embodied emissions to go from a permanent temporary to a permanent system. What that did is that eliminated all of our subgrade foundation walls. It alleviated a lot of unbalanced lateral loads on our diaphragms, and it significantly reduced the thickness of the subgrade diaphragms. So that was a lot of concrete that was removed from the project by collaborating with the geotechnical engineer and seeing how better to manage geotechnical subgrade loading. So that got us from 0% to about 4%. And where we wanted to go from there was use a lot of fly ash, pozzolanic material like slag to reduce the cement content of all of our mixed designs. So this was partially it was a back and forth between the client, the contractor, a potential supplier, discussing the pros and cons of all of the fly ash content of all the different mixes we had. So the final decisions got us close to 10%, and then we discussed carbon curing with the client as well. As you can see, that would have been about a 1 or 2% reduction beyond what we had achieved up until that point. This is an example of a project in a corporate park in Texas. The reason I put this project in here was to show an example of a project where the baseline building, the construction type of the baseline building was very obvious. This project was in a corporate park where all of the other buildings were tilt-up concrete. So in this case, it's very clear to us that the baseline building would be tilt-up concrete. So we have something to compare to. For the previous project, it was a little bit more challenging to determine what a baseline would be that would actually meet all of the criteria that we were designing for. So we used the project itself at concept phase. Some sources of reductions here in embodied carbon were, of course, fly ash and precast concrete elements. That's low-hanging fruit. Another source are design changes. As you can see, a very aggressive cantilever in the top image. That was tempered to cantilevered canopies over an entryway that retains some of the same design language without quite as much structural embodied carbon. So there are a couple different sources here. I'm going to go to the next slide. All right, so this is LaGuardia Airport. This is a New York project out of our New York office that I worked on. And there were several really interesting strategies that were taken here to reduce embodied carbon. One, again, the low-hanging fruit, fly ash in the foundations, and it may depend it may be quite region-specific what your baseline level of fly ash inclusion is. In the Northeast, it isn't quite as high as it is on the West Coast. So using 25% fly ash did actually represent a reduction from the baseline in the Northeast, but as as the quality of sustainable construction continues to improve, that baseline also moves. So you're chasing a bit of a moving target. Another couple sources of reductions here were a geotextile membrane was used to control groundwater uplift forces. So that reduces the number of tension piles needed. That's a reduction in foundation concrete volumes. And there was also a delayed base connection construction sequence for the pedestrian bridges. That is an unexpected source, oftentimes, of embodied carbon reduction, but a lot of times the size of the foundation is significantly increased to manage temporary construction configurations. So this was a strategy to reduce the forces on the foundation, and it in turn reduced the volume of concrete required and the embodied carbon. And actually that's not even included in the numbers you see here. So this was everything except the delayed base connection strategy of the bridges. I'm going to head to the next slide. So construction administration. So as I'm sure everyone here is on this aware, starting an LCA during CA is no one's ideal scenario, but it's never too late. You can get more reductions out of a project, even if you have to start an LCA and CA. So this is a university biological research building. This graphic just kind of indicates all the different ways you can break down the embodied carbon in your building to kind of pinpoint where the low-hanging fruit is, where the big ticket items are. So you can pinpoint it by life cycle stage. You could pinpoint it by building system. You can see the exterior walls and the slabs are pretty big portions. Or you can pinpoint it by material. So this was a concrete building. It's no surprise that concrete is the lion's share of the embodied carbon. Oftentimes, even with steel superstructure buildings, concrete can be the majority of the embodied carbon because of cement being such a high embodied carbon material, and foundations representing a very large percentage of the total structural material quantities. Also important to note, if you're looking at the facade versus the structure, sometimes it's very often 45% to 50% facade and maybe 60-65% structure. So it may seem like the facade would be insignificant compared to the structure in terms of the carbon breakdown, but it really isn't. It can come very close to 50-50. And in the facade, if you're looking for the low-hanging fruit, aluminum components are typically the low-hanging fruit. Yeah, so we can go to the next slide. Okay, so this is, I'll try to race through these. This is an example of the results of the analysis that I did for this project with the rest of the rest of the project team. And we went through all of the submittals that the supplier had provided to us, and I analyzed them to provide them some feedback on which one would be best for the project. And of course, it may seem we would want the highest fly ash mix. We did. But the challenge is on this project that the construction schedule was such that even a little bit of fly ash would increase the amount of time they would need before demolding certain or removing formwork. And that was a significant increase to the overall construction schedule. And that's something that made us realize it's really important to discuss as early in the project as possible that you would want pozzolanic materials in your concrete, such as fly ash, because it does impact construction schedule quite significantly. So we were able to find a happy medium. What the contractor wanted to know is what is the impact of choosing this submittal over that submittal to the overall carbon footprint, the embodied carbon of the entire project. So this helped them do that. So we got from a 0% baseline, a 0% fly ash, which is what the contractor had initially wanted to use to keep a very tight construction schedule, get very high early strengths, which structurally we don't need. We designed for 28-day strengths. So they wanted those high strengths really early so they could move from floor to floor really quickly. But we found a great happy medium. They were able to make 25% fly ash work. So it just goes to show show that doing a life cycle analysis in CA, working with the contractor, can still get you embodied carbon reductions. And they liked being included in that process as well. Some really quick notes. We decided to incorporate this into our general notes. So right at the beginning of the project, everyone's on the same page as to what our embodied carbon goals are on a material level. For example, this is a concrete mix design schedule for our general notes. Other points on this page that are noteworthy is this graph can just help illustrate how much the global warming potential of different concrete mixes can vary by region, depending on the local fuel mix and other factors. There are some technologies available, such as carbon curing, which it reduces embodied carbon to a similar extent that using fly ash would. So you could use fly ash and in situ carbon curing to get possibly double the carbon reductions you would get with just one of those strategies alone. There's also carbonated aggregate, which is in the pipeline. It's not quite as widely available yet, but you can get much greater carbon reductions with carbonated aggregate than you can with in situ carbon curing, but they're both really great options. So if you can use all of the above, then why not? So I would stay tuned on carbonated aggregate to see how that scales up. Sustainability in steel. The take-home message here is it's really important to specify a minimum recycled content in your specs, because by the time a supplier is being brought on board, it might be a little bit too late to ask at that time. Oh, carbon curing. Yes, I have a question from David about what carbon curing is. So that's when liquid carbon dioxide is pumped into a concrete mix, and that carbon dioxide reacts with the cement and the other mineral binders to form carbonated minerals. So you're essentially locking away that carbon dioxide forever in the mineral of your concrete matrix. Carbonated aggregate is a little bit different, and that reaction happens in a plant, and it happens with the aggregate itself, which is then just brought to your local mixing facility and mixed into the concrete. So they're two slightly different processes. If you want more technical information on either of those, Carbon Cure, which is a company, their website will have more information on in situ carbon curing, and Blue Planet Aggregate, their website will have more information on carbonated aggregate. So more about sustainability in steel. There are different furnaces that steel comes from. There are electric arc furnaces, there are blast furnaces. Typically electric arc furnaces have much lower embodied carbon. They use much higher recycled content. So by specifying your minimum recycled content in your specs, you can help ensure that the source of the steel for your project is coming from a mill with lower embodied carbon than others, because as you can see, it can vary significantly. Hopping to the next slide, I just did a bit of a data dump on this slide of different carbon reduction strategies that we've used on different projects. So you can feel free to take a screenshot of this, and if you have any questions, let me know. That's all I have, Jackie. Thank you.
Thanks. You might have to relinquish control for me to get it back. And we are going to be sharing these slides, so no need to take a screen share. We will be sending them out after the session as a PDF from all the presenters. So let me switch back to my other screen here. And we also have other resources towards the end of the session that we'll also share with you. So I'm going to open this up to questions. Devki went ahead and answered the question that David put in the chat, but if there's anyone on a cell phone or on the phone and can't type into the chat, feel free to unmute yourself and ask a question. Or you can put them in the chat box if you don't want, if you're not able to unmute yourself. While that's happening, I guess I have some questions. I think each of the presenters spoke a little bit about benchmarking and baselines. When we do energy modeling, we have like a very clear way of benchmarking or comparing buildings, right? We use EUI as a square foot basis, and there's a correlation between the size of the building and the systems in the building to how it performs. Is there an equivalent for embodied carbon aside from like LEED saying find a building that's similar? And that's open to any of the presenters. Yeah.
I can jump in on that one. So embodied carbon is typically benchmarked for better or worse, also using area takeoff. So we tend to report embodied carbon in kilograms of CO2 equivalents per metered square. Some folks will put that in square footage if they need to, but kilograms of CO2 we tend to report on climate change in metric internationally. So it might be good to get used to those units. The Carbon Leadership Forum conducted a benchmarking study back in 2017 of about 1,000 buildings and came up with some kind of rough ranges that we tend to find buildings fall within. It was really a part one study, and it's one that we're looking to update. There was a lot of challenges in terms of data collection and aligning scope, and also background data sets, et cetera. So we're really excited and trying to move forward to update that benchmarking study. So that would be providing benchmarking figures of embodied carbon per building type and maybe regionalized benchmarking as well. But currently right now, there is no CBEX for embodied carbon. So I think the other presenters might have different opinions on this, but I think there are, it's pretty widely acknowledged that this like self-referential benchmarking is really important, like was said in the presentation, for really specific buildings like an airport or a hospital where the types are quite complicated. But for most building, it's really a matter of real dearth and scarcity of data, right? And it is really kind of a gamble of convenience. So I think the industry is really moving away from that kind of self-declared benchmark and towards a more quantifiable numbers, which many of the certification schemes or some of them already do. So.
Okay, so we do have a, thanks, Steph, that helps put it in perspective of what's available and what's not. We did have a bunch of questions come in. I guess I just needed a little bit of an icebreaker. I'm going to work backwards here. So John Cassidy just asked, can the speaker speak about how small firms or sole practitioners might start to engage with embodied carbon? It's a, is there any tips or tricks that you can speak to?
I was going to make one suggestion. So I think if you were just starting out and had never thought about embodied carbon before LCA, I think something like EC3 is great as a tool because you're able to just create a quick login and look up products that you use, that you specify on projects. Try to find something that's close to things that you're very familiar with in your practice and start to get a feel for what those numbers are, and then start branching out maybe to other manufacturers that also have EPDs in that space so that you can get kind of a relative scale to what it is that you're specifying and impacts that you can make on a smaller basis. So maybe not tackling a whole LCA study, but those smaller bits of impact that you might be able to make.
And that's a really great segue to Scott Schell's question, because he's stating that he was surprised by facades being about 40 to 50% embodied, like representing 40 to 50% of embodied carbon. And he mentioned that they found that Kynar coatings were much higher than anodized. So, he's looking at a very specific coating of a larger system and looking at the embodied carbon of that. So his question is, can you elaborate on the key factors that we can focus on to reduce facade emissions?
I could list a couple. One would be, I think I mentioned this briefly, but aluminum tends to be the highest embodied carbon material in most of the facades we've looked at. So anything you can do to reduce the aluminum quantities or find alternatives, maybe even wood framed windows. I suggested wood framed windows on one of our really big projects, and I got laughed out of the room, but we might have to do things that we're not used to doing, or things that we think of as vestiges of the past to actually reduce embodied carbon aggressively. And then another one would be precast facade. There are many projects I've worked on that have precast facades, and a lot of the times it can be hard to get fly ash into those mixed designs because the supplier and the client are concerned about that resulting in a non-uniform color. So as a result, you end up with a massive amount of concrete used in a relatively non-structural way that's very heavy and doesn't have fly ash or slag in it. So I would recommend to find alternatives to those.
I guess if to add on to that really briefly, yeah, I think those of us who are super excited about LCA also tend to like get excited about like really getting into the analysis, right? I know I certainly do when I present on Tally and like getting into the details and have like a real joy in that. I think I just wanted to underscore that it is totally possible to reduce the embodied carbon of your project without doing any analysis. Like we're not quite there yet with like a prescriptive approach for carbon reductions, although we know that we really need for this to be a totally accessible practice, we need to have both a prescriptive and performative based approach like we do with operational energy. For a lot of folks that I talk to, the gateway is, just to underscore what was said before, is low carbon specifications. So many different materials and associations already put out low carbon spec language that you can adopt. You don't have to make it from scratch. I would encourage architects to bring up the topic with your structural engineers. You may be surprised, they might already be doing this on other projects. So before you even get into really advanced analysis, you can really also be thinking about, as was mentioned before, can I write language in to get lower carbon concrete, to get lower carbon steel? I guarantee you probably have concrete and steel on all of your projects, even if you're not, trying to have that special mass timber building, et cetera. The other material I just wanted to give a shout out for is insulation. I think it's another one that folks tend to overlook. And another strategy that can be very straightforward is also becoming aware of super high carbon materials. So XPS, for example, is one of the most carbon intensive and damaging products you could be using on your projects. So really thinking about what because of the blowing agents traditionally used in that type of foam insulation. So I think finding opportunities to look at what your standard assemblies are, looking at your specifications and thinking about where you can make, a dent and start familiarizing yourself with the materials that you already use is a really great first step that might be more accessible for some folks.
Thanks, Steph, for mentioning that. We also saw good results finding alternatives for foam insulation.
Yeah. Awesome. Thank you. So the next question is from Daphne, and I think it ties a little bit into what Steph was just talking about with regards to specifying the right type of concrete or steel. So Daphne's question is, how do you specify recycled content in steel? And how do you know, like, is this a common practice or a growing practice to know exactly what percentage of recycled content will result in reduced embodied carbon?
Devki, you want me to take the steel question? Do you want to take it? I mean, there's a lot to say about steel and decarbonizing steel.
You can go ahead, and I might add a little onto the end.
Sure. I guess one, in the interest of promoting resources, there's some really good resources that you can find online about low carbon steel specifications and thinking through the ins and outs of steel manufacturing. It's quite a complicated topic. And so I really appreciate a lot of the tips that Devki threw out there about thinking about, for example, which steel shapes tend to use which manufacturing types. And that can be a really important thing to know that can change the embodied carbon of your steel structure, whether you're using tube steel, hot rolled steel, et cetera. That often working with your structural engineers on that topic can be really, really helpful on projects. The American Steel Institute has a decarbonization pathway guidance for architects that is super helpful. After I'm done talking, I'll drop a link in the chat. It's a great document to read and think about. It kind of has top 10 tips for getting lower carbon steel on your projects. Recycled content is the trickiest one, I would say, and one that is actually kind of rife for a lot of debate. There is a scarcity of recycled content. So it's similar to aluminum in some ways, so recycled content is cheap, everybody wants it. Steel with higher recycled content is cheaper to make, so manufacturers want to use it, and then they can also use electric arc furnaces, which use electricity, so they have lower carbon. So it's sort of win-win-win. One of the tricky things with recycled content, even more so with aluminum, is that to some degree, if you're speccing really high recycled content material, you're kind of just taking it away from other projects. So it's a little questionable whether your particular building might look lower carbon, but it's a little questionable whether you've actually made any carbon reductions in the world by doing that. Although that is like a very contentious thing to say probably. And having improving the marketability of low carbon and high recycled content steel is certainly something that a lot of American manufacturers and buy clean legislation is very interested in. Often the carbon footprint of steel also has a lot to do with the geography. So where that steel is made, what the electricity mix of that country is, and how much coal versus other sources of fuel, like all gets wrapped into those carbon figures. So it's recycled content is actually a pretty tricky topic, but a really interesting one.
Devki, did you have anything to add, or do you think Steph covered it?
Well, that covers it.
Okay, awesome. We do have two more questions, and they're both tool related. So we have a question from Aishu asking, what tool would you recommend for MEP systems, especially during the DD or CD phase? And I don't know, Kayleigh, if you want to take that. Okay.
Yeah, happy to take that one on. I'm a mechanical engineer by background, so this topic is very close to home for me.
With Philly ties, right?
With Philly ties, I know.
Yeah.
It's all coming full circle. So MEP specifically is really lacking information, especially on the EPD side, and especially in the United States. We are so lacking information there. What you can focus on for MEP, because rather than saying there's no information, don't do anything. Focusing on refrigerants, really important, because you can make a huge reduction in your embodied carbon just by changing to a next-gen refrigerant. If you look at our 410A versus a next-gen refrigerant, you're immediately making a huge impact on the project. Or looking at the different pipe type materials you could be using, copper versus PVC versus PEX versus carbon steel, anything like that, where you're just comparing apples to apples. And material reduction, of course, makes a big impact. But I think in terms of tools, since that was the specific question, OneClick does have quite a few MEP materials. They are not local materials. They are French EPDs that you might see there for a microwave or a hand dryer or random things that you'll see. Things are covered by the scope of all of the different EPDs globally. You could do an MEP study for sure, but it might not achieve the result that we would like, which is reduction of embodied carbon. It may achieve an LCA study as a whole. So I think just focusing on where you can make an impact is really key for MEP.
Awesome. And then the second tools question is from Shannon, and this is for Stephanie. Can you further describe the workflows for the to build or not to build tool that examines promoting retrofits? I'm interested in that too.
Yeah, I can. I probably, to some degree, I probably shouldn't mention that tool because it's not publicly available yet. But it's one I'm super excited about, and I think is going to be available very, very soon. It's probably going to launch at Greenbuild or shortly thereafter. So it's a good one to look out for. And another similar tool is Epic, which is also going to launch at Greenbuild and at COP26. So both of those, I'll kind of describe them together in a way, even though they do slightly different things. They're both early phase design tools, or even are aimed to be used at concept design or pre-design, whatever we want to call it as well. So they're both going to be browser-based tools, and they're going to draw from LCA studies that are putting carbon figures on building typologies. So with to build or not to build, it's going to let users explore a range of strategies they might use on their projects. And try to look at what the operational savings might be versus embodied carbon savings. So for example, it's going to look at, rather than you having to model every single little piece of your building or already have a design, it would let you do an assessment that said, okay, what kind of savings would I expect if I keep 30% of the structure, or if I keep all of the structure, right? If I do like a major renovation versus a minor renovation. So a lot of work is going into thinking about what those scenarios actually are, so they can be really useful. Similarly, the strategies are connected to how much of the building and existing fabric is retained, are also connected to strategies for mechanical system upgrades and green energy retrofits. So the idea is that you could pretty quickly be able to start looking at those trade-offs from a cost perspective, from an operational energy perspective, and from a carbon perspective. Both in terms of embodied carbon and operational. So at the Carbon Leadership Forum, this is the request we hear the